The crisis in physics, why the Higgs boson should not exist. The discovery of the Higgs boson in 2012 at the Large Hadron Collider, LHC, was hailed as a triumph of modern physics. The particle, proposed nearly 5 decades earlier, was confirmed to give other particles their mass through the Higgs mechanism. However, this discovery has not resolved the crises in physics. Instead, it has deepened them. There are several reasons why the existence of the Higgs boson as we understand it might be problematic and could signal an underlying crisis in our fundamental theories of the universe. 1. The hierarchy problem. One of the most pressing issues in physics is the hierarchy problem, which concerns the vast discrepancy between the mass scale of the Higgs boson and the Planck scale. The Planck scale is the energy scale at which gravitational effects become as significant as quantum effects, and it is approximately 17 orders of magnitude higher than the energy scale associated with the Higgs boson. According to quantum field theory, the mass of the Higgs boson should be extremely sensitive to quantum corrections from virtual particles, potentially driving it up to the Planck scale, unless there is some mechanism to cancel these corrections out. The standard model of particle physics does not provide a natural explanation for why the Higgs boson has the mass it does. This has led to the introduction of various theoretical frameworks, such as supersymmetry, SUSY, which propose new particles that cancel out the quantum corrections. However, despite extensive searches, no evidence of supersymmetric particles has been found at the LHC. The lack of such particles suggests that either SUSY is invalid, or that the scale of SUSY breaking is much higher than initially thought, further exacerbating the hierarchy problem. 2. Fine-tuning and the universe's fine-tuned constants. The existence of the Higgs boson with its observed mass implies a high degree of fine-tuning in the fundamental constants of the universe. For the universe to support the formation of atoms, stars, and ultimately life, the mass of the Higgs boson must be within a very narrow range. If it were even slightly heavier or lighter, the properties of the universe as we know it would be profoundly different, potentially rendering life impossible. This fine-tuning is problematic because it suggests that the universe's fundamental constants are not arbitrary, but are instead carefully balanced to allow for our existence. While fine-tuning is not necessarily a flaw in the theory, it is philosophically and scientifically unsatisfying. It raises questions about whether there is a deeper underlying theory that explains these constants, a possibility that current physics has not yet uncovered. 3. The vacuum energy crisis. Another critical issue related to the Higgs boson is the vacuum energy crisis, also known as the cosmological constant problem. The Higgs field contributes to the vacuum energy density of the universe, which is related to the cosmological constant, a term in Einstein's field equations that represents the energy density of empty space. According to quantum field theory, the vacuum energy density should be extremely large, far exceeding the observed value inferred from cosmological measurements. The discrepancy between the theoretical prediction and the observed value is so vast, approximately 120 orders of magnitude, that it is one of the most significant unresolved problems in physics. The existence of the Higgs boson and its associated field exacerbates this crisis because the Higgs field's contribution to the vacuum energy density is non-negligible. Resolving this problem may require a fundamental revision of our understanding of quantum field theory, gravity, or both. 4. The need for new physics. The Higgs boson's properties, as measured at the LHC, do not show any significant deviations from the predictions of the standard model. While this is a testament to the model's success, it also highlights its limitations. The standard model does not account for gravity, dark matter, or dark energy, which together make up approximately 95% of the universe's energy density. The lack of new physics beyond the standard model, despite extensive searches, suggests that either new particles and interactions exist at energy scales currently beyond our reach, or that our current theoretical frameworks are incomplete. The Higgs boson, in this context, serves as a reminder of the gaps in our understanding of the fundamental laws of nature. 5. Theoretical justifications and alternative models. There are alternative theories and models that challenge the necessity of the Higgs mechanism as the sole explanation for particle masses. For instance, Technicolor theories propose that the mechanism for generating particle masses arises from a new strong interaction rather than the Higgs field. Similarly, extra-dimension theories suggest that the Higgs boson could be a manifestation of the geometry of additional spatial dimensions. While these theories are speculative and have not yet been confirmed experimentally, they highlight the need for continued exploration and the possibility that the Higgs boson may not be the complete story. The crisis in physics lies in the fact that we lack definitive evidence to support or refute these alternative models. Conclusion: the discovery of the Higgs boson was a monumental achievement, but it has not resolved the underlying crises in physics. The hierarchy problem, fine-tuning, the vacuum energy crisis, and the need for new physics beyond the standard model all point to fundamental gaps in our understanding of the universe. The existence of the Higgs boson, with its observed properties, should motivate us to seek deeper, theoretical insights and new experimental approaches. Only by addressing these challenges can we hope to uncover the true nature of reality and resolve the crisis in physics.